Hey guys, thanks for hosting me, Harsha. Today I'll be talking about some work that my team and I have been working on for the past year or so. This is our UniReps workshop paper that we presented at the past UniReps, titled "Winning Tickets from Random Initialization: Aligning Masks for Sparse Training." So just these are my collaborators that I worked with. Adnan's a PhD student at the University of Calgary and the Vector Institute. Ikanch is a PhD student at Vector, and Professor Yanni Ioannou is my supervisor. So we'll first begin with some background. That's, I'd say, pretty important for motivating this field of study and just to bring everyone up to speed on this domain of work. We first begin with this idea of weight symmetry in neural networks. So this is a pretty interesting idea that's been established for quite some time, since the 90s. On the screen, you can see just two, like a simple feed-forward neural network, where these are your bias elements, and you have these two inputs, x1 and x2. And I'm just trying to show the connections between neurons in this figure, shown by these yellow lines. And it outputs some output y hat. And you can see in the first figure that, okay, sure, these arrows are pointing here. And in the second figure, you can actually, these neural networks, typically they have the usual parameterization of these neural networks exhibits weight symmetry. What that means is you can actually reorder the neurons in each layer, which does not change the underlying function that's being computed by the network. So in just these two simple figures, I've just reordered the way these paths are moving, or swapped these two neurons, and the output is still functionally equivalent, but these points lead to different, these outputs lead to different points in weight space. So in your loss landscape, these 2 points could be very different from each other, although these functions are isomorphic, or they're functionally equivalent. So just to reiterate, we can swap the hidden units, and we can still have like functionally equivalent models, but again, different points in weight space. So this is just a very simple example that I've shown. Just a two-layer like hidden network, hidden layer feed-forward neural network. But if you just imagine, if you scale this to very large networks, where you have to move, or there's a lot of possible configurations to permutation indices. Example, in ResNet-20, there's over 10 to the power of 55,000 ish permutation symmetries, which is a considerable amount. So the intuition this leads to is we can permute a network which remains functionally equivalent to its original configuration. Now, formally described, as I mentioned, in the 90s, it was claimed that these neural networks are permutation invariant. So they possess this weight symmetrical property where you can swap any two neurons and the underlying function doesn't change. So these permutation symmetries have been connected to being a source of non-convexity in the loss landscape. You can think of this as you can have a function lead to one point, or you can have your data and your entire optimization lead to one point, and you can have another minima, which is simply just a copy of that minima. What that means is that since these neural networks, by properties of overparameterization, are connected to be non-convex, we have global minimas at different points in weight space due to this idea of weight symmetry. So we can think of one minima just being a copy of another. Formally, if you want to think about it, mathematically, if you have a multi-layer network with d-1 layers, and each with n neurons, there is precisely n factorial to the power of d-1 possible permutations that you can compute. Now, you may ask, like, why do we really care about this, and why are permutation symmetries important. So a simple topic of study, or that's been spoken about in optimization and this like general like realm of research that quite interested me, was if you take two independently trained models, so two identical models that you train on the same data set, and they have different initialization and different batch orders, just by the effectiveness of SGD, typically, I shouldn't say always, but typically we're able to observe very similar training trajectories. So if you plot out train loss versus your epochs, you can typically see this similar like training graph. And this is quite interesting because we work in such a non-convex loss landscape. Now, this idea of why this happens has been connected to permutation symmetries, because as permutation symmetries are one of the source of being in a non-convex loss landscape, it connects to overparameterization being one of the reasons behind the abundance of having a large number of minima. And you can have multiple different functions, because as we spoke about before, you can have these two functioning equivalent y hats that fit the data similarly, but they lead to different points in weight space. So you can still have multiple minima, but you have these different functions, which are still functionally equivalent, that lead to different points in weight space. Now, this idea of this behavior of these training dynamics connects to the idea of something called mode connectivity. Now, what mode connectivity is a pair of trained neural networks are said to be connected or linearly connected if the loss along the linear path between the networks remains small. And this phenomenon of mode connectivity was first observed in the context of SGD, where they took two neural networks trained from the same initialization, but different data orders, and that exhibited linear connectivity. Now, that was very early on, and later on, Frankel in 2020 showed that independently trained neural networks can be linearly connected. Now, this was quite interesting as to how how we're able to form a connection between these two independently trained neural networks. So in 2021, and Tezari et al., they observed that while they took a model and its randomly permuted counterpart, so they just took a model and a random permutation, that's what we spoke about before, which are functionally equivalent, and he's found that they're rarely linearly connected in the weight space. So this presents this idea of a misalignment, and it presents that you need this idea of a loss barrier between two networks. So he had made a pretty bold conjecture, which is a pretty strong hypothesis, where he said that there exists a linear path between SGD solutions if permutation invariance of neural networks weight space is taken into account. I describe it with some little visuals here. Just for a little disclaimer, don't really take these basins, these solution basins, literally. Your neural network loss landscapes don't look like this. I'm just trying to illustrate if you just had two networks, call it theta A and theta B, how they would behave. So just to highlight Tezari's conjecture, if you have independently obtained SGD solutions, call it theta A and theta B, they exhibit no loss barrier when accounting for permutation symmetries, suggesting that all SGD trained networks converge to a single basin modulo permutations. So what that means is a lot of words to unpack, but what that means is suppose you have for each pair of trained networks A and B. So you have some network that you trained A and I trained some network B on the same data. Of course, different initialization and different data order. There exists a permutation of the hidden units of each layer of B such that there's a linear path between, or an almost linear path between theta A and pi of theta B. And that's of non-increasing loss relative to the endpoints. So what that means is if you interpolate between theta A and theta B, if you look at the midpoint, typically a midpoint is seen at alpha equals 0.5. What we'll see is that you have a large error barrier when you interpolate between theta A and theta B. So it would be termed that theta A and theta B are not linearly mode connected. But if you look at theta A and pi of theta B, when you interpolate between these networks, you'll see that there's a very small error barrier, or the error barrier is being close to 0, which would be termed that these points are linearly mode connected. So this is a bold hypothesis that was pretty rigorously tested by Antazari et al. And soon after, in 2023, Gitri Basin came out, works that you might have heard of. They came out and they supported this conjecture that neural network loss landscapes often contain nearly a single basin after you account for all permutation symmetries of these hidden units. And their primary contribution was proposing a way to find these permutations, pi. And the way they proposed to find this, although this problem has been out there, it's a typical combinatorial optimization problem. They took the original weight matching problem. Weight matching is just a permutation matching algorithm where you can find this permutation. And they broke this problem into a so-called linear assignment problem. So our problem is a greedy solution. So you are never going to find the perfect permutation, but always an optimal or a approximation. The next thing that is a little different than weight symmetries, but is important for our research is pruning. So as many of you might be familiar with, we can prune networks that achieve comparable performance to the dense model using some pruning strategy, such as IMP or wriggle or set. There's many sparse pruning algorithms out there. And in this work, we focus on unstructured pruning, which is based on the concept of dropping or pruning out the smallest magnitude weights, as opposed to removing neurons or filters, which is called structured pruning.
Rohan, sorry to interrupt. I think there's a question.
Oh yes, for sure.
You can.
Is the bold claim that once you take the permutation into account, that the non-convex optimization problem becomes convex optimization problem, or almost convex optimization problem?
No, I shouldn't say that the optimization problem becomes convex. It's just stating that if you take, he's basically saying that if you take in account for permutation symmetries, all of your SGD solutions will technically converge to a single basin, since each basin is is a functionally equivalent copy of another basin. So if you have n basins, you can think of like n1 being just a copy of n2, which is a copy of ... all the way up to n-1. So it all leads to being converged. It all leads to SGD solutions being converged into one solution basin. If you take
Isn't this... Please continue.
No, sorry, go ahead.
Please continue.
Oh, okay. Yeah, so I was talking about just how we focused on unstructured pruning, just sort of described in this figure, where you can remove weights, specifically smallest magnitude weights. And we use IMP, which is a pretty well-known algorithm, where it works by training the full dense network and then pruning out a fraction of those weights with the smallest magnitude. There's a third step which can or cannot be used, which is reinitializing the remaining weights back to their original values. This is called weight rewinding, and then repeating the same procedure for a number of times. Now, you may ask, how does pruning connect to weight symmetry? So an interesting observation is that unstructured pruning, so pruning out weights, actually breaks weight symmetry, while structured pruning does not. And we'll get more into that later on. So we now get into studying the dynamics of like sparse training and the problem we're sort of interested in focusing on. So what sparse training is trying to train these neural networks with a lot of their weights removed. Now, what the original sparse training problem is suppose you start from some dense initialization. Call it, I'm just gonna put some easy notation just so we can follow. Call it A0. We train that network to convergence, call that AT, and then we prune that network using IMP, as spoken before, to get our mask MA. And now suppose one of you guys samples some random initialization, and now we want to train, let's call that B0, and now we want to train the initialization you guys had with our mask. So our goal is to train this, but typically this doesn't work very well. It doesn't generalize as well as the dense or the pruned solution. And this is what we're focused on for this project, as how could we actually possibly do this? But before we get into this, of how we could train this, an attempt to solve this problem is, which many of you guys may know, is lottery tickets. So in 2019, the lottery ticket hypothesis was proposed. And this was a pretty big contribution, I guess, in this community, where they suggested that sparse networks exist within these dense models. And when trained, they can achieve the same performance as the dense model if you start from a suitable initialization, which is the caveat. So they proposed to solve the sparse training problem by reusing the same initialization as used to train the pruned model. So for very small models, training from such an initialization maintains the generalization performance of your pruned model. And it demonstrated that you could actually train with a highly sparse mask. This was back in 2019. And later on, since they were only able to show this worked for very small models on pretty simple data sets, later on they showed that to find lottery tickets or to find these winning tickets for larger networks, they required weight rewinding. So the only difference between the last slide and this slide is, instead of starting from a completely random initialization, you actually start from a snapshot, you could say, of the initialization used to obtain your pruned model. So there's still information being passed between this and this. So moving on, we can now get into the motivation for our work. So just to recap, sparse training from random initialization with a fixed mask leads to typical poor generalization performance. And then we had the LTH, which was there to try to solve this problem. But again, LTH was, the caveat of LTH was, first you need a dense model that must be trained to get a mask. And then this mask is only usable with its original random initialization. So, and it required weight rewinding as well. So it was a pretty expensive and not very practical for training sparse models, as it could also not be applied to new random initializations. So the question we ask ourselves is, how can we use these winning tickets from LTH, so the mask that you obtain, with a different random in it? So we try to understand why LTH does not work for different random initializations from a weight space symmetry perspective. And we show that once permutation symmetries are accounted for, it's possible to reuse the winning ticket mask with different random initializations. So you may now ask a few things. One thing could be, why do we need to permute the mask, and what importance do we get by permuting the mask? We sort of try to describe it, visualize it in this figure over here. So this is just a simple, just to visualize a simple setting of a 2D loss landscape of a model with just two parameters, W0 and W1, and we operate on a single input scale. This dotted line in the middle is just trying to show how these symmetries work. You can have this basin which is symmetric to this basin. So this is just for illustration purposes. So the first the first figure is showing that we can start from some WA, some initialization, dense initialization. We can train this to convergence and obtain a mask. So this is just illustrating how we can obtain a mask. Now, due to permutation symmetry in weight space, as mentioned before, there are many functionally equivalent loss basins. And if you have a new random initialization, WB, that can land in a different loss basin, equivalent up to symmetry. So we showed that LTH fails to generalize well with a new random initialization, primarily due to a mismatch between the optimization basin of the winning ticket mask and the new random initialization solution basin. So what that means is, if you have some random initialization WB, now this might land in a completely different basin, which is still functionally equivalent to your original basin. And if we apply our mask, MA, what typically might happen, or what we hypothesize, is that you land in a different basin, which is equivalent up to symmetry, but not the solution basin that we're trying to train within. But permuting the mask in such a way, you can actually still land in the basin of your random initialization and still train within that basin to get better generalization performance. And we'll move on to the method on how we actually obtain this permutation and talk about our training paradigm in more detail. So for a quick overview, there's been many neural alignment algorithms which are used to locate permutations to bring hidden units of two networks into alignment. So after Git rebasin, there's a work titled Repair, where they focused on understanding the source of poor performance of these standard deep networks, such as ResNet-20, VGG11, where their weights have been linearly interpolated between pairs of networks with aligned neurons. So what they basically found was these interpolated networks, these merged networks, they suffer from this phenomenon of variance collapse, where the hidden units have significantly smaller activation variance compared to the corresponding units of the networks from which they were interpolated from. So we have adapted this activation matching from Repair and modified it to our usage and made it generalizable to all types of models. And the problem of activation matching is, again, just a linear sum assignment problem, which corresponds to maximizing the matrix of correlations between pairs of hidden units in these two networks, and can be solved by a typical Hungarian algorithm. And once again, these permutations that are generated is just an approximate, you can say. It's not the perfect permutation. Solving for the perfect permutation is an NP-hard problem, which has not been solved yet. So of course, we just go by a greedy approach for all of our work. Now, I'll just so that we're consistent moving on, this is our training procedure, or what we sort of did. I'll highlight it in these 5 steps, where we first start from some random initialization, WA, and we train that to convergence, and then we prune it. We prune that with IMP, or you can prune it any way you want to obtain your mask in the cheapest possible way. And step 2 is now, we're in the sparse training realm. So step 2 is establishing your first baseline of the LTH. So this is just standard lottery ticket. As mentioned before, since lottery tickets typically work better at starting at a rewound point, so starting at some k greater than or equal to 0, typically strictly greater than 0, you need to start from some early snapshot just to get better performance. It's still a very interesting problem as to how you can start at true initialization, but you start at some early rebound point k, and you train this solution. Our third step is you now sample a different random initialization WB. And this is the sparse training problem that we spoke about before, where you're trying to train WB from some rebound point K, just so that we're consistent with LTH. We will start with all value. We will start all experiments at some rebound point K. Yes, Harsha?
So when you speak of the LTH solution, you're talking about like multiple levels of IMP at this point, or just one sort of step, like with some ratio?
Oh yeah. So for LTH, it's just now at that point. I'm calling it LTH, but it's just training the mask of A with the initialization associated to getting that mask.
Okay, makes sense. Yeah, thanks.
Yeah. So it's not trying to find a lottery ticket again. It's just doing the training A with A, basically. So step 3, just to highlight again, is the problem of sparse training, which is trying to train that mask of A with non-associated initialization. Step 4 is now training WB, because typically matching does involve training between 2 fully converged models, which is something that I'm interested in looking at further, as to not having to train your second model to convergence. But for now, we train both to convergence, and then we perform activation matching to bring WA close to WB in solution space. So we're finding a permutation such that if you apply that permutation to WA, you can say that WB and pi of WA are linearly mode connected. So great, we have found a permutation. Now, the difference between step 3 and step 5 is we're now applying that permutation to the mask. And this is the solution that we're interested in obtaining. And we want this permuted solution to be as close to the LTH solution. And of course, be better than the naive. So for this workshop work, just for the workshop, we just had a few experiments. We used VGG11 on CFAR10. We used some ResNet-20 models on CFAR10 100, and lastly, ResNet-50 on ImageNet. So the first experiment, which is pretty standard in this line of work, is to test on VGG. I'm not sure why it's always done with VGG. I guess because VGG is just so vastly over-parameterized, it's easy to match. So I guess so, yeah. And since it's easy to match these VGGs, we use this VGG11, which is slightly modified. So in fact, we just, rather than having multiple fully connected layers at the end, we just had one fully connected layer. And the classifier was set up for 10 classes rather than 1,000, as VGG was originally meant for ImageNet. So we can first see that at a very moderate sparsity level, when you start off, by the way, this purple line is your dense baseline. So when you start off at a rebound point k equals 0, it is almost very close to each other. And even for throughout testing for all rebound points, even up to 50, it remains pretty close, where your green line is your LTH, and the permuted and naive are pretty much all close together. But upon increasing your sparsity, so now you have a lesser or relatively less overly optimized network. At k equals 0, it's still a problem, but upon increasing the rebound point, we can start to see a little bit of a difference between your your permuted solution and your naive solution. In fact, you can also see that after a certain rebound point, it really doesn't matter between 50 and 10. It's often pretty stable, but your permuted solution, the blue line, proceeds to still improve upon increasing the rebound point and gets pretty close to the LTH solution. So that was just for VGG11, and now we wanted to test this on ResNets. So we first started with the ResNet-20 with the width of 1, so just standard ResNet-20. Now, what we observe in these dynamics, sparse training dynamics for ResNet-20 is, again, at a very moderate level sparsity, everything was very close to each other. There was not much difference, and LTH was performing far better than both the permuted and the naive. And although the permuted is slightly better than the naive for most parts, there is still a very large gap between your LTH solution and your permuted. So this is when we started to look into larger width ResNets. It's been shown in theory and in practice that larger width ResNets, when you try to interpolate between them, there's better linear mode connectivity. So that is what we did. We started to increase the width of our ResNets. So the first row is a width of 4, and the second row is a width of 8. So again, at k equals 0, it is still pretty difficult to train. But upon increasing your rebound point, and as increasing your sparsity, we do see that there's a gap between the LT permuted and the naive is more significant. And in fact, when you increase the width to 8, it's even more significant, where your permuted solution is now getting closer to your LTH, and your naive solution is now differing far away from your permuted. So we could see that increasing width did help in obtaining better permutation, or you get a better match between two models when they have higher width. We tried this on a little bit more of a difficult task, CFAR 100, which consists of 100 classes. It's better to see more significant gaps between these sparse solutions. So again, we started with the width of 1. The problem at k equals 0 still persists. So as did with lottery tickets originally, so you have to start from some rebound point. Again, the rebound point is, of course, ideally you want to train from the smallest, as close to 0 as possible. So you could see that although we did test for all the way up to like an early snapshot of 100, it really doesn't matter. You could still start from 20. It remains the same, more or less. But you can see that for width of 1, LTH and permuted were still very far apart. As increasing to width 16, that gap does get a little bit smaller, and the naive solution does proceed to get much worse for extreme levels of sparsity. So we could see that the idea of increasing the width was helpful even for CFAR 100 experiments. The next experiment that we worked on was ResNet-50 on ImageNet. So again, we try to evaluate the performance of the permuted mask at different sparsity levels on ImageNet. And ImageNet consists of 1.28 million images across 1,000 classes. So in this experiment, the dynamics looked a little bit different. We observed that the permuted solution does outperform the naive across all sparsity levels, showing that our hypothesis does hold on large-scale data sets. Now, while the permuted solution performs better than the naive, there is still a significant gap between the LTH and the permuted solution. If you just focus on rebound points 10 and I think 25. So there's still a pretty big gap between these solutions. And this could possibly be because the permutation matching not being accurate enough, as only a small subset of your training data was used for activation matching. So And just to iterate again, this purple line is your dense baseline, which is trained for, I think, 90 epochs. So each sparse solution is trained for 90 minus k epochs. So this was trained for 90 minus 10. This was trained for 90 minus 25, and so on. So this is something we're still interested to explore and further improve. We're also trying with just a slightly larger width ResNet-20, so with the width of 2. And I'll talk about in the analysis how that is improving. But yeah, just since ResNet-20 is such an expensive model to train and obtain a permutation with, we just focused on with the width of 1 for now. I'll talk a little bit now about some of our analysis. We start with studying the model width. So larger width typically exhibits better linear mode connectivity. So that's why we increased the width throughout our experiments. In figure A, you can see ResNet-20 on CFAR 100 or CFAR 10, sorry. And we can see that the error barrier interpolating at 0.5 starts to decrease. So again, just for a quick remark, we obtain your loss barriers, or you check for a spike in between your models at 0.5. That's because during linear interpolation between a pair of independently trained networks, it represents the midpoint in the interpolation where the weights of the two networks are equally merged or blended together. Also at alpha equals 0.5, the weights of both networks contribute equally to the interpolated model. So this is the most direct way to test how well the two solutions align in terms of their learned representations. So we can see that throughout increasing the width, and even for ResNet-20 on ImageNet, with the width of 2, you can see that your loss barrier has decreased as compared to with the width of 1. So one thing to note is that you can never actually get an exact loss barrier equal to 0. So in the loss landscape, you could try to imagine that this is possibly not being in these two solutions not being exactly in the same basin, but very close. And again, studying the geometry of the loss landscape and behavior of SGD solutions is still something that needs to be more studied. So again, just to take with a grain of salt that these loss barriers not being exactly 0 does not can mean that these solutions are not exactly within the same basin, but closer together. And I show this a bit better in our loss landscape analysis. So we showed that modulo permutations, reusing that permuted mask leads to convergence in the same mode as LTH. So this is just standard 0-1 loss landscapes we took a ResNet-20 model with the width of 4 on CFAR 10. And our permuted solution is the green star. So this is sort of to help visualize that we're not exactly within the same basin. Like being in the same basin would, or as what we think would be being very close to, this is the LTH solution, this star right here. You're in the same mode, you could say. So we're in the same mode, but we're not quite within the same basin. So this was just helpful to get an idea about how our permuted solution behaves compared to the LTH solution. And just to highlight that you could reuse, it's possible to reuse the permuted mask and still be in the same mode as your LTH. And we're further going to extend this to show how your naive solution will be not in the same mode, or it would possibly be in, as you can see, just within the color regimes, that you might be in a higher loss region. And thank you. And that's all I have, and happy to answer any questions.